Do we have any questions on oxidation reduction reactions? How to determine the oxidation numbers? Would we like an example?
So, when you follow the steps, like in the reaction, do you start on the left side and like determine, like if it's a covalent, like for example, H2O2 goes into H2O plus O2.
Okay.
How do you know how do you determine which oxygen is going to be that, have that oxidation number of -2?
Okay. So I start with one compound at a time.
So you start on the left?
It doesn't matter. I could start here if I wanted.
Okay.
You just need to find the oxidation number for each atom in each compound. Okay? So this one right here is 0 because it's all by itself. Yeah? And then on this one, this is a covalent compound, so we have to check, does it have hydrogen? If not, does it have fluorine? If not, does it have oxygen? And so on, in that order, right? So it has hydrogen, so its oxidation number is +1. And then since there's 2 of them, that's a +2. Plus 2 times whatever it is for oxygen, right? And the total has to equal what? In this case, 0, because this is a neutral compound. You with me? So we subtract 2 to both sides and then divide 2 to both sides, and we get -1. You following? So a lot of times oxygen is -2, but in this case it's not. Most of the time it is -2, but you always need to check. Okay? And then you do the same thing on water. It's going to be +1, and it's going to turn to be +2 here. All right. So we want to find out which one is oxidized and which one is reduced, right? So this one here goes from -1, and you're wondering, well, should it go to this one or to this one, right? Well, let's go to this one first and see what happens. The charge is reduced, right? So therefore this is reduction. Or this oxygen is reduced, right? And then if you go from here to here, because you can't really go from here to here because it's on the same side, right? This one right here is, well, it gains electrons, so it's oxidized. So this oxygen is both reduced and oxidized. Does that make sense? If there is an oxidized, there is a reduced, and vice versa. Other way around. Okay? Which one is the... So in this case, hydrogen peroxide is both the reducing agent and the oxidizing agent, right? It causes reduction and oxidation. So that one's a little different, but anything else? What's the easiest way to tell if it's an oxidation reduction reaction? If it's not, what type of reaction? Double replacement reaction. It's the easiest way. But then we found you still have to check, right? Because sometimes it's not an oxidation reduction either. Okay? All right, ready to move on to double replacement reactions? Ready or not, here we go. Double replacement reactions. And there's 2 types of reactions that are double replacement. What are they? acid base and precipitation, okay? So that's been a min since we talked about it, but so this just a general example. AB plus CD are the products. Because in the end, you're going to have to predict the products here. Do you remember what happens in a double replacement reaction? They swap partners, right?
Yeah.
So A hooks up with who?
C.
C or D?
A, B, C, D.
With what? D. Why not C? Because the first atoms in an ionic compound are cations, and cations can't come together. We're good? So it's going to be A, D, and C, B, cation first. Ekri.
Is this chapter 5 or 6?
This is chapter 5. Yeah, we didn't quite finish last time. Are we comfortable with double replacement reactions? Maybe after today we'll be more comfortable, right? All right. So this is both precipitation and acid-base reactions. Let's start with precipitation reactions. Anybody remember how we can tell if it's a precipitation reaction over an acid base? Yeah, go ahead, Lucas. If a solid forms from two, not just liquids, but two aqueous solutions, right? Water solutions. And since it's an aqueous solution, that tells us it's what kind of compound? Ionic or covalent? Ionic. And the reason why is because what does aqueous mean? It dissolves in water. Now, covalent compounds can dissolve in water as well, some of them. But what aqueous means, it's a solution of water where the ions dissociate one another, okay? We're not going to say we have an aqueous solution of sugar. I mean, I guess we could, but I don't remember ever seeing that. So, all right, so we start with two aqueous solutions, and the example we did was PbNO3. This is an aqueous solution, plus potassium iodide. Can anybody tell me what this is called? Lead 2 nitrate. Good. Okay. And then we swap partners. Can you guys come up with the formulas? We just was tested on this. How'd that go, by the way? So lead. Good. KNO3. Is that the correct formula for KNO3? For potassium nitrate? Yeah, that's a 1-to-1 ratio. Potassium is 1 plus, nitrate is 1 minus, so we're good. We have to check. We can't just, oh, this has a 2, I'm going to carry that 2 over. Don't do that. Do not do that. And PbI2. This is lead 2 plus. We can tell by figuring the charge out. So remember, lead and tin are variable cations, like the transition metals. So you have to check. Iodine is just 1 minus. Cross the charges, simplify. All right. Now we've got to determine. We know we know this is a precipitation reaction because we did it in class, right? We got this yellow precipitate to form. You guys remember what a precipitate is? When a solid forms mixing two liquids, okay, or two aqueous solutions, I should say. So which one is it? If you remember, you might remember what we said it was. which one was the solid. But you're gonna have to memorize all these? Kind of. Not too bad. So we have to learn about which ions are soluble and which are not, and sometimes they are and sometimes they're not, depending on what they're with. Let's keep it as simple as we can make it. So have the different, we'll just say, I'm making a table here, soluble ions. And I'll give you the exceptions, because it seems like there's always exceptions. Well, sometimes there is. All right, if the cation is a main group element, group 1 element. What are the group 1 elements called? Alkali metals, right? So if it's an alkali metal ion, so we're talking about includes hydrogen, H+, Li+, Na+, etc., right? These guys are always soluble, no matter what they're with, without exceptions. That's cool. So if an ionic compound has group 1 element in it, it's ionic. It is soluble. It's also ionic. Okay? Now why is that? Why are those guys so special? Do you remember anything about the group 1 elements, the alkali metals? I did a few examples. Highly reactive, right? These guys are going to react in water every time without fail, okay? And then we have a few polyatomic ions. NH4+ is soluble. Nitrates are soluble. NH4+ is ammonium. Nitrates are soluble. Perchlorates are soluble, ClO4-. Acetates, C2H3O2-. And is that all? Yeah. And there's no exceptions here as well. Woo. So far, so good. No exceptions. We like that. So ammonium is the only cation, polyatomic cation, right? So, okay, there we go. And then nitrates, chlorates, perchlorates, and acetates. Always soluble. Then we got the halogen ions, or halide ions. Chlorine, bromine, and iodine. Notice fluorine's not on there. Fluoride is not always soluble. It's partially soluble most of the time, but it's not always soluble. Yeah?
And the group 1 ions, is it just those 3 that are,
No.
that it's all?
All of them.
Okay, that's what.
Yep. Okay, any other questions? Okay, there are exceptions with the halide ions. Silver+, lead 2+, and mercury 2+. Which, I don't know why I put this, we hardly ever see that. But it's one of them. So these are the 2 main ones you need to know for that. So in our compound here, we have iodine is in there, but it's with lead 2+. Therefore, that's a solid. Good? This one has a group 1 element, group 1 ion, and nitrate. So it is soluble without exception. So that's aqueous. Does that make sense to everybody? If it's soluble, we put AQ next to it. If it's insoluble, meaning it's not soluble, we put an S next to it for solid. We okay with that? Okay. And one more. Sulfates, SO4 2 minus. These guys are soluble, except with lead 2 plus, mercury 2 plus, so these two, and two other ones, barium 2 plus and strontium 2 plus. Notice they're not all the 2 pluses, but all of the exceptions have a 2 plus charge. Hg2 2 plus, mercury 2 plus.
You said that halide ions doesn't include fluorine.
Yeah, it does not include fluorine.
Doesn't have
Just those three. Yep. Now I can give you another list to say which ones are insoluble. Let's keep it simple here. Let's just say, yeah, go ahead, Mariana.
If it's with, if those two are together?
Yeah, if we have a compound, for example, if we have lead 2 sulfate, is that soluble or insoluble? Insoluble. These guys are soluble unless bonded with these ones. Does that make sense? So if we have magnesium sulfate, is that soluble or insoluble? Why? This is soluble unless it's bonded with one of those. Is magnesium one of those? No. Therefore, this would be soluble. And this one is insoluble. Do you following me? Understand what this is saying?
I don't understand this one now.
Okay, so if a compound has one of these ions in it, it is soluble unless these are the cations
Oh,
that's bonded to those. Make sense?
yeah.
Thanks for asking. And if it's not on this list, what should we say? Insoluble. This is the soluble ones. If it's not on, if you can't find it on this list ever, then it's insoluble. Yeah.
Is that why magnesium is? Because magnesium is not a group 1 ion.
It's not a group 1, but it's not soluble because magnesium. It's soluble because of sulfate,
It's not one of the exceptions.
and it's not the exception. Yep. Thanks for clearing that up. Any other questions on how we read this chart? And you need to know this chart. If you want to put it on your little reference card, do it, but how are we coming on our polyatomic ions?
You have to find it inside.
Got to get these down. You're going to run out of space on your little card. Okay? Besides, if you know all this stuff up here, it actually makes your life easier. Just saying. All right. Any questions on the solubility chart? So solubility means what? I didn't give you a definition. Soluble means dissolves in whatever you're talking about, but in general we talk about dissolving in water. Dissolves in water. And insoluble is just the opposite. The prefix in is not dissolve, does not dissolve in water. dissolve. Yes, sorry.
Not dissolving.
Okay, and we're going to use this chart, have this readily available until you get it down. Should we do some examples? Okay, example 1. Who can tell me what that's called? Ammonium nitrate. Soluble or insoluble?
Let's see the lesson.
What is it? Soluble, so we put what in parentheses? AQ. We're good? Dissolves in water, forms aqueous solution. Example 2. Lithium hydroxide. Aqueous or solid? What makes it aqueous? Lithium is a group 1 ion. Always soluble. Good.
And hydroxide is not an exception, so.
And there's no exceptions for group 1. That's right.
Oh, right.
Yep. Example 3. PbCl2. Solid or aqueous? Solid, because the lead 2 plus is an exception.
So it's not soluble.
Not soluble, insoluble. Good? And then example 4, we have iron 2 hydroxide. Soluble or insoluble? Insoluble because it's not on our chart. So we're going to say that's a solid. So why are we doing this?
To learn.
Yeah. So we can determine if we have a precipitation reaction. So let's do a real example. In real life, we're not going to just do that. That's maybe just a partial step in what we do, right? So if we have AgNO3 is an aqueous solution, and we have sodium chloride, also aqueous. I want to predict what products we will get. Can you do this on your own, or do I need to show you through this one? Oh, I need to show you? Okay. So, since we have 2 aqueous solutions, what happens when it says aqueous? What does it mean? And what does that mean? Dissociates. The ionic compound dissociates in water. And so now you got a bunch of ions floating around. And if you have any 2 ions that will form a soluble or insoluble substance, it will come together and form a solid. Okay? So what type of reaction is this if we have 2 aqueous solutions as our reactants? It may or may not be precipitate. It might be acid-base, but what is it always? Double replacement reaction. And that's going to help us to know how to predict these. Okay? So the 2 cations swap partners, right? That's what happens. So silver, what's the charge of silver in silver nitrate? 1 plus. That means it's going to stay 1 plus in this reaction. And it's going to hook up with who? Chloride, which is 1 minus. So what's the chemical formula for silver chloride? AgCl. Is it solid or aqueous? Is it soluble or insoluble? Insoluble, because chlorine is one of those that has an exception, and silver 1+ is that exception. So that's a solid. And then sodium hooks up with nitrate. What's the charge of sodium? 1+. What's the charge of nitrate? 1-. So what's the formula? Aqueous or solid? Aqueous. Is this a precipitation reaction? How do we know? Because it forms a solid out of 2 aqueous solutions. Good? Yeah, Lucas.
Yeah, in the reactants with silver nitrate, I thought as long as there was a silver 1+ ion, then it would have been insoluble, right?
Well, let's see. That's an exception for halides only. Nitrate, there's no exceptions. So
It's only if they're in that same category.
that's right. Yep. Thanks for asking. Everybody clear on that? Now,
Clear it up.
is sodium nitrate produced in this reaction? What do you think? Yes? The other option is no. What do you think? So Chad thinks yes. What does everybody else think? Yeah? What does AQ mean? It's not liquid. It dissolves in water. What happens when it dissolves in water? It splits. It's split. It did not come together. It's still dissociated. Now, if we get rid of the water, it'll probably come out, right? So, but there's no reaction for this part. But this part right here does react. And it comes out as a precipitate, kind of foggy, as we saw that yellow substance, right? This one isn't yellow, this one's white. Not clear, but white. And you don't have to remember that, but okay. So let's show what happens during this reaction. So we have our container of solution, of water, and you throw silver nitrate in it, what happens? It dissociates, it breaks apart. So we got silver plus ions and nitrate minus ions. You with me? Does this one break apart? Because it's aqueous, it's going to break apart into sodium ions and chloride ions. Now I'm just drawing one of each, right? How many are there really? Trillions of them, right? Okay. So when this happens, these guys say, okay, they're going to meet up. Because they produce an insoluble, not those ones, sorry. Not those ones. These two, right? They're going to hook up and form that solid. These two are going to stay dissociated. So how do we write this in a chemical reaction? Because this is kind of bulky and messy, right? Well, this next part's going to be kind of bulky and messy. We're going to call it a complete ionic equation. So if we do this, we're going to split up the ones that are aqueous. And it's going to split them into Ag plus, because it's not going to just be solid silver. This is an ionic silver, okay? So we're going to say it's an aqueous solution, plus nitrate is aqueous. Y'all see what I'm doing? I'm splitting this one up right here. Just like I showed you right here, splits up. This one right here splits up, sodium chloride. So we're going to split up a sodium ion from a chloride ion. And then we come over here to the product side. Is this going to split up, silver chloride? No, it's a solid. So we're going to write it as is. And this one splits up because it's aqueous. There's sodium ions and nitrate ions. Can you see it all? Okay. So that's the complete ionic equation. That looks yummy, right? Right? No. So this is just a step that we take. In fact, when we're done, I'll show you how to do it without doing this, if you'd like. Okay? But it's nice to know what is happening here. Okay? So these split up, and this is the only product that is formed. Good? All right, so now let's write the net ionic equation. You guys know what the word net means? The part where you throw the basketball. So you guys all have jobs, I'm sure, right? You guys pay taxes? And they say you're going to get paid $30 an hour or whatever, right? And then do you walk away with $30 an hour? No. That's your gross pay, right? But your net pay is what you take home, right? After all taxes are removed. Well, we're not removing taxes here. Instead, we're going to remove spectator ions. What's a spectator? Someone who just observes, right? They're not participating in the chemical reaction. All right. So can you determine which ions are the spectator ions? Which ones are not participating in the chemical reaction? Sodium and nitrate. There's sodium and nitrate ions on the left. There's sodium and nitrate ions on the right. Nothing changes. So those are our spectator ions. So we remove those. If they're the same on both sides, mathematically we can subtract them on both sides, right? We don't have to, we just cross them out. Good? And what are we left with? Our net ionic equation. Silver plus, chloride minus, and silver chloride. So basically this is what's happening, right? We good? So we don't have to worry about the other stuff and just make it simple. Simplify it. Any questions on how to write that net ionic equation? Could I have done this without writing the complete ionic equation? Yeah. We can see that this is my only product, right? There it is. And what's that product made of? Silver ions and chloride ions. That's it. Then just make sure it's balanced before you use it, right? Okay. Any questions on precipitation reactions? Should we do one more? Yeah, pull out your worksheet that you had from last time. Does anybody need one? Uh-oh. No, that's the wrong binder. Anybody need one? She needs two, one for you and one for her. Yeah. Okay, this is section 3 on the back side. No. Nope, not 3. Not section 2. Section 2 just says classify which type of reaction it is, right? Section 3 is determine the oxidation numbers. Section 4 says determine if they're aqueous or solid, right? Or soluble or insoluble.
Section 4, tell me that the.
Should we practice that real quick?
Which
Okay,
one?
section 4.
Yeah, can we do the CR2, CO3?
CR2, CO3, 3. Yeah, let's do it. All right, so we got to determine if this is soluble or insoluble. What do you think? Insoluble because it's not on that chart. It's not on our insoluble chart that we just made. So if you know these if you know these in your brain, you don't have to look up anything. Makes it easier. But let's get there. Okay? It's not a whole lot of stuff on that chart. So this is soluble, insoluble, so I could just put a solid there, right? Or you can write insoluble, either way. Do you want to do another one? Or do you want to do all of these?
One more, Na2, CO3. That's also insoluble.
Why? Why is it insoluble?
Because not on the list.
Is sodium on that list?
Yes, I just saw it.
Yes, sodium is a group 1 ion, and it is always soluble. Therefore, this is aqueous. Does that make sense? So you're going to have to check back to that chart we created until you get it down. No guessing. That doesn't do anybody any good. Do you want a couple minutes trying some of these? Or do you want to move on? Yeah, Chad.
Earlier we did the example of iron 2 hydroxide. Oh, that's a solid. Never mind. That would be insoluble.
That's right. Yep. Any questions? Yeah.
Said if it's not on this list we made, then it's solid?
It's insoluble, therefore creates a solid. Yep. Now, is that 100% true all the time? No, but for this course, good enough. Okay? And for the most part, it is the way it is. And there's probably a few minor exceptions, but it's pretty good. Any questions on section 4? Or tell me if you want more time. Or do you want the answers?
Here's answer sheet
Yeah.
Silver perchlorate, that would be
Since perchlorate is in there, is there any exceptions for perchlorate?
chlorate now.
Then that means it's soluble.
Silver, but silver
Yep.
is an exception.
Silver's just the exception for the halides. Yep,
Yeah.
that's it. Okay, there are the answers. Just to check to see if you're getting this. I'll be right back.
how many hours we have to spend to learn that. So, 10 hours and a half. 15 hours. And where I just take and 4 to 17 or something. Do you have extra credits? Lab is harder.
Oh, yeah, the exceptions, so this is important to know. Is that all soul sins?
Okay, any questions on those? All right, let's do examples from section 5. Which one do you want to do? I'll let you do the other two.
Can we do the first one?
Yep. Do you have a question? Yep. This is also on Canvas, but okay, yeah. Yeah, someone have a question?
For
Yeah.
the net ionic, do you always include the charges?
Yes. It's called an ionic equation because it's made of ions. Because what happens is they dissociate and become ions, right? So they're floating around in water as ions. That's why we write it. All right, so it says predict the products of the following reactions, balance the molecular equation, write the net ionic equation. Notice it doesn't say write the complete ionic equation. You don't have to do that step. But if it helps you, then write it. NH4Cl plus lead 2 nitrate. All right. Tell me what the products are. Anybody, somebody, one buddy, yeah.
So it'd be,
Good. Somebody else. What else? What? PbCl. Is that the formula PbCl?
Two.
PbCl2. Because this is a 1 minus. There's 2 of them. -2, +2. This is a 2 plus ion. You with me? So we still have to know that, guys. All right. So what about sodium nitrate? Is that aqueous or solid? Aqueous, good. Both cases. What about lead 2 chloride? It's a solid. All right. Now that we have this, is it balanced? Can we balance it? I hope so. Where are we going to start? Ammonium nitrate. Okay. There's how many ammoniums do we have, or should we do all of them separately? Polyatomic ions, 1 ammonium, 1 ammonium. 1 nitrate, 2 nitrates. We better put a 2 right there. We just changed the nitrates, so we better put a 2 over here, yeah? We just changed the chlorine, so there's 2 there, 2 there. 1 lead, 1 lead. We're good. Okay? Now what?
Now the last one.
Net ionic equation. What's the product that will form here? Lead 2 chloride, the only solid, right? These guys are all aqueous. Uh-oh, that's aqueous. So PbCl2 as a solid. And how do we get that? 2 chlorides. And 1 lead 2 plus ion. Good? How are we feeling? Okay, it's still balanced. If we balance it, it's still going to be balanced when we write the net ionic equation. Why don't you try the other 2? Unless, do you have any questions on this? Please say something if you're not understanding something. Be here for you and no one else.
You just showed the product of 2 chloride, PPP, not the, you just showed the.
Yep, we don't need to show this. Why don't we show these guys?
You are not happy.
Because these are spectator ions. They do not participate in making this.
Okay, only the 2Cl and PPP participated to make a new product.
Uh-huh.
What is the name of this?
This is a net ionic equation.
Yeah, but what is this molecule?
The lead 2 chloride,
Yeah,
that's what it is.
yeah, it has a name like sodium.
Lead 2 chloride, that's the name. What?
It's a solid with a powder.
It is. It's a salt. It's different salt than what we eat, but it's a salt.
It's a salt they use in heavy water to cool down the water.
I don't know what they use it for.
They use this salt.
Do they? I bet Google would tell you. Yeah, I don't know.
But it's good to know. I'm going to write it's a kind of salt.
All ionic compounds are salts, right? This salt happens to not dissolve in water. Would you like the answers or not yet?
All ionic compounds are salt?
Mhm. That's just another name for it.
But it's not our table salt.
Yeah. There's only one table salt, and that's sodium chloride.
Maybe it's a sea salt because it's salty.
Yeah. Sea salt is sodium chloride.
I have to watch the video for it.
Tables or road salt's not sodium chloride. Calcium chloride, I believe.
You put some classification of lines between PP and S3. You made a table and then you delete charges.
Oh, I'm not sure what you're asking.
You put a charge for PV and whatever the charge for PV is plus 2.
So this one right here is that.
Oh, yeah, no, it's not.
NO3. This is nitrate. You know the charge of nitrate?
Charges, base charges. If we don't know charges, that
Right.
is
So this is a 1 minus charge.
1 minus, it's a 3 minus. No, 6 minus.
2 of them.
6 minus.
Plus 6.
So it's
1
minus
minus
2 minus.
2, that's negative 2. So this side has to be positive.
Positive, balance this out. Exactly.
There's only one lead. That means it has a charge of 2 plus.
2, and then they cancel each other.
Yeah. Yeah.
This equation, we have to know the charge, and we have to know which one like each other, then we can combine. Otherwise,
Swap charges and, yeah.
but the cation first, the cation on the second cation first.
Yeah. Uh-huh. We good? Do you have a question? Okay. Don't. All right. Oh, let me put these answers up here real quick for you.
It's easy for me to write this quickly, but if you could explain the last one, that would be nice.
Yeah.
I don't wanna say something.
All right. So this one here, sodium and barium swap partners, right?
Yeah, so
Sodium chloride and barium sulfate. Barium is a 2 plus ion. Sulfate is a 2 minus. Cross the charges. Make sure you do it correctly. And then you balance it. And since this one right here, that's a solid because barium is the exception for sulfates. Is one of the exceptions. That's why it's a solid, so that's our product. And it's made of barium ions and sulfate ions.
So I knew this with barium and then the sulfur with chloride. But they disappear only right?
They don't disappear,
Only
they're just floating around in there. They don't come together.
they do barium and sulfur to get together and then still stay away.
It's not that they're away, they're still in there. They're mixing around.
But these two are
That's right.
getting
They're attracted together because they're insoluble in water.
so this is the formula.
Yep. This is the net ionic equation.
I'll write this
What?
I like this chapter.
You like it? Good. Good. Any questions on these? Yeah.
So, like, for the second one, how on the left it's 2KOH, how come you do the subscript on the right? Versus like
So why is this here?
yeah,
What's the charge of copper?
in this case it's positive.
2 minus, -2, +2. It's a 2 plus ion. So when it comes over here, it's still a 2 plus ion. Because it's the same ion, right? Then you swap charges, and you have to put parentheses because hydroxide is a polyatomic ion. There's more than one. Good? Andrew,
I know we're moving backwards. Why is
you're good.
Cu a 2 gas? Oh, because I wrote.
Well, we have to figure it out. This is a
Oh, no.
transition metal, so we got to figure out its charge.
Okay. I was looking at the wrong thing.
Yeah, if it's a main group element, we don't have to figure it out. Just look at the periodic table, right? Okay. Anything else? You ready for acid base? Or do you have any other questions? Not ready?
We are ready in 5 minutes.
All right, let's do this.
Acid base.
Acid base.
That's
All right. Can anybody remind us how we know a compound is an acid?
more hydrogen.
Not more hydrogen. Hydrogen is the cation. Okay? Not just an element in the compound, but a cation. For example, is CH4 an acid? No. This is not even an ionic compound. That's a covalent compound. They're shared. It doesn't create a cation. So that is not an acid. And how do you know if it's a base? For this unit, anyway? If hydroxide is the anion. That's it. And this is specifically for what type of reactions? Neutralization reactions.
Is it OA or
OH. Hydroxide.
neutralization?
Okay, let me give you a few definitions. An acid is a proton donor. What makes somebody a donor? Someone who has money or someone who doesn't have money? You have to have money in order to donate, right? Okay. Same thing with an acid. What do they have to have in order to donate? Protons. Oh, whoa, hold on a sec. Can a compound donate a proton? Let's draw the Bohr model for hydrogen ion. For hydrogen by itself, there's one electron, right? How many protons? One. How many neutrons does most hydrogen have? 0. It's hydrogen 1, and you didn't have to know that, okay? So most hydrogen is, did we talk about protium, deuterium, and tritium in this class?
Next chapter.
No? Okay. No big deal. I really didn't? Oh, man. Failed you guys. No. Doesn't matter. But okay. So if hydrogen loses its only electron, what is it now? A proton. So the hydrogen ion is a proton. So we call it a proton donor. So this proton is just a hydrogen ion. And that means it has hydrogen ions to donate. Is that an acid?
Yes.
No.
It's a base.
That's a base because it has hydroxide. What about that one? Is that an acid? Why not? It doesn't have any protons to donate. It doesn't have any hydrogen ions to donate. So these are not acids. What about H2SO4? How many protons can it donate? Two of them. It has two to donate. It doesn't mean it will donate both of them, depending on the reaction. So when we have an acid base or a neutralization reaction, we're dealing with strong acids and strong bases. And for this unit, that's all we're dealing with, okay? We'll talk more about what makes a strong acid, strong base in the last unit, okay? So for example, we have sodium hydroxide as an aqueous solution with hydrochloric acid as an aqueous solution. So which one is our acid? Well, I just told you. We have an H+, it's ready to donate, and it does donate it. Right? Kicks sodium off and comes over here. This is a double replacement reaction. How can you tell? Two aqueous solutions, just like precipitation, right? And so what do we get? NaCl and HOH. What's another way to write HOH? H2O. Is sodium chloride soluble in water? Is it aqueous or solid?
It is soluble because
It is soluble because of sodium, without exceptions, right? So that's aqueous. Is water aqueous? Does water dissolve in itself? No, it is itself. So we call water a liquid. You with me? For all double replacement reactions, we should be able to write a net ionic equation. Can anybody write this net ionic equation from what you learned just a minute ago? What's the product? Is this a product? How do you know? Because it's aqueous. It's still dissociated. It's not formed. Water is our only product. And how do we get water? H plus and OH minus. And I'm writing this aqueous just so that you know what it is. Okay? As we do the stoichiometry in next section, then don't really have to write it, just so you know what's going on. Okay? Should we do another acid-base reaction?
We still call that a net ionic.
Yep, this is a net ionic equation. Get rid of the spectator ions, still has spectator ions, right? Sodium and chlorine, not really doing anything. Okay, let's say we have H2SO4 and lithium hydroxide. determine the products, balance it, and write a net ionic equation for it.
H2 goes Li.
What's that?
H2 is not AT.
H2 hooks up, the hydrogen hooks up with who? Hydroxide, and lithium hooks up with sulfate. So what product do we get over here? What did you say? H3O? Are we going to get H3O, guys? Great question. We will not. Why is this 2 right here?
Too high.
Because it's hooked up with sulfate, which has a 2 minus charge. We cross the charge, and that's why there's a 2 right there. If it goes and hooks up with hydroxide, it's not going to need 2 of them. It's going to be H plus and OH minus. This is a 1-to-1 ratio, and we get what? H2O as a liquid. You with me? And we get lithium hooks up with sulfate. What's the formula? Li. What's the charge of lithium?
2.
By itself? Ion?
2 positive.
Just a 1 positive because it's in group 1. Always use the periodic table. Don't just go with your memory on this. There's a lot of stuff on that periodic table. Use it. And sulfate is SO4 2 minus. What do we do with the charges? Cross them down. And we get Li2. Do we need to put parentheses around SO4? No, because there's only one of them. Is that soluble or insoluble? Soluble because it has lithium and it has sulfate. And lithium's not the exception. Okay. How are we feeling? Yeah.
Could you demonstrate how you got H2O again?
Yep. This is a double replacement reaction. This hydrogen swaps partners with lithium. So H plus, that's the charge on a hydrogen ion, because it's in group 1, so it's plus 1, right? Hydroxide is always OH minus. Cross the charges, it's a 1-to-1 ratio. We could say HOH, but how many hydrogens are there? You with me?
Yeah, so I guess I was confused because it's H2, but that's from the sulfate.
That's, this 2 is from the sulfate, yes.
Okay, that's what I was confused.
That 2 is because, well, I just put them together, right? If you want, you can write HOH, no big deal.
And I was confused about further up where
Yeah.
it's, when you, yeah.
Where does the 1 hydrogen go?
Yeah.
So it looks like you have 3 on the left and then 2 on the right.
Yeah, we good? Do we understand that? Okay. All right, is it balanced? One sulfate, 1 sulfate. 1 lithium, 2 lithiums. Oh, we better put a 2 right there. Where else do we need a 2? Front of water. If you balance like that, there's 2 hydroxide and 2 hydrogens, right? You don't have to worry about it that way. You can break it up one element at a time. Should I redo that one? No? Okay. So what's our net ionic equation, guys?
Equation
the net ionic equation. What's our only product that forms? Water. Do I have to have two of them? According to what it says, right? And how do I get that? With two hydrogens and two hydroxides. Is that as simplified as far as it goes? Can I just get rid of those twos? So it looks like we didn't need a balanced system, but no big deal. What do you notice? In all neutralization reactions, what is the net ionic equation? That one right there. Always that. Good? Yeah, Andrew.
That's what I was gonna ask, but also, so all acid bases, the product is liquid, and all precipitations, the product is solid, right?
And it's not just any liquid, it's water. Yep. But yeah.
Would you get a 2H, like, in 2H plus? Yeah, it's like the charge is always 2 is
The reason there's two of them is because of that two right there. That tells us there's two hydrogens, right? That's why I put it there. This two tells us there's two hydroxides, so I put it there. And there's the two right here, so I put it there. Now let's always keep it simplified. Divide everything by two and it's still balanced, right? We good? Any other questions? So what do we get when we have a neutralization reaction or an acid-base reaction in this unit? We get water and we get salt. Is that a salt? And there's a salt. We get salt water. You have the strong acid, strong base. You mix it in the right proportions, you could drink it. Don't. But you could. You'd have to know it's mixed in the right proportions, right? And can we do things perfectly as humans? No. So don't drink it, okay? How are we feeling? Okay, you got some more practice on section 6. Says, predict the products of the following reactions. Identify the acid and the base. Write a net ionic equation that will occur when these mix. We have just 1 minute till break. Let's practice. I'll put the answers up on the board. Okay, go ahead and take a break, or you can keep practicing.
how to put them together. I'm still confused on that. I know how to know if they're insoluble or soluble.
Okay,
but
good.
I don't know how to.
Do you know where to separate the cation from the anion? Draw a line that separates the cation from the anion. Can you do that? Okay. Do you recognize what that is?
Yes, that's.
Polyatomic.
Yeah,
And that's the only cation that's a polyatomic ion.
okay,
There's the cation, the rest is the anion.
okay,
There's the cation. How do we know that's a cation? Because it's a metal.
okay.
That's a polyatomic ion, that's the anion. Metal, non-metal, cation, right?
Anion.
So that's where they're hooked together.
Okay,
Does that make sense?
yes,
Okay. And so this one right here, we have to know that that's a NH4 plus ion. We just have to know that. If you don't know it, you better have that little reference card available for you. But I would get that down.
yeah,
Okay, get those polyatomic ions down. Otherwise, we're gonna move on and we're gonna learn more stuff
good stuff,
and not have enough room on that card.
yeah,
Okay, so this, do you understand in a double replacement reaction, the cations swap partners?
okay,
So that means this cation's gonna come over here with this anion. This cation's gonna come over here with this anion.
okay,
Does that make sense?
yeah,
So that's what a double replacement reaction is. And so to know what the chemical formula is, we write this, so just for, these are still gonna be ionic compounds. So we write, okay, this is NH4 plus, is gonna hook up with NO3. Why is that 2 there? That comes
It's
from
2.
this, right? So it's NO3 minus, because that's what the formula is for nitrate.
okay,
There's a 1-to-1 ratio. You bring down the 1, bring down the 1. We don't need to write ones, so that's the chemical formula for it.
okay,
And if you don't know the charge of this lead, because it's a variable, this is -1, right, for nitrate.
mhm,
There's 2 of them, that's -2. This is +2. It has to be the same number, just opposite charge to balance out.
okay,
Does that make sense in your mind?
yeah,
Okay. There's only 1 lead, so it takes the whole charge. So lead 2 plus is going to hook up with chlorine.
yeah.
And what's the charge of chloride?
-1.
Yeah, -1, so 1 minus. And so Cl 1 minus, bring this 1 down here, this 2 down to here, and that's why we get PbCl2.
Okay,
Just like we did at that last unit, okay? It's just,
okay,
we're going to keep having to do that,
okay,
okay?
okay.
Does that make sense?
Yes, that helps a lot. So, and when does it always work like that, that I just,
Yep, for a
Switch
double
these.
replacement reaction, how you know? Because it's 2 aqueous solutions, 2 ionic compounds. They're always going to swap partners.
okay, when they're both aqueous?
Yes.
Okay.
Uh-huh.
So that was my other question, because I try to look at
These ones?
these, yeah,
Okay,
like
yeah.
these, and they're not like
So
crossing.
since this is not a double replacement reaction, that tells us it's an oxidation reduction. These 2 right here are double replacement.
Okay,
Since that's not a double replacement reaction, because they don't swap partners, right?
they're oxidation reduction, so
Yeah.
it's single, okay.
So we don't,
We always change when they're both the same, no?
when they're both aqueous.
Aqueous,
Uh-huh.
and if it's just.
But if you look at this H hooks up with the nitrate, Ag hooks up with the chlorine. They swap partners. That's how we tell it's a double replacement reaction. That means this has to either be precipitation or acid base. And how do you tell the difference? If it makes a solid, it's precipitation. Do you remember I
Okay.
mixed those 2 liquids and it made
Yeah.
the yellow solid?
Mm-hmm,
That's a precipitation reaction.
okay,
If it makes a solid, that's precipitation. If it makes liquid water, that's an
That's
acid
acid
base. But you have to have an acid and you have to have a base.
okay,
And that's how you tell acids and bases.
okay,
Good?
yes. And that was my question. So, for this one, we know acid is always gonna be H,
Uh-huh.
and the base is always
For this unit, yep.
okay. Even, is it always gonna be like that, even if they have another compound next to it? Or does
There's
it
the-
matter?
There's the H. There's the OH.
Mhm.
The H has to be out in front. It
Okay.
has to be an ionic compound in aqueous solution, and it has to be in front. In front, hydroxide.
Mm.
For this unit, yes, that's how it's gonna be.
That sounds good. Okay.
When we get to chapter 10, we'll learn more.
Okay. Fine.
Okay? So get it down now,
Mhm.
and then we won't have to relearn this, right?
Yes. Okay. Thank you.
All right, thanks. All right, one more minute. Yeah, let's see.
I tried to remember them, but they're arguing.
I think Amon might have an extra card. If he doesn't, then just
Write
cut
down
a
on
piece
the
of paper out that size. Yeah, that's okay.
I don't know why I forgot. I forgot my.
Is that all you needed? Is that all you needed? Okay.
Other than that, everything I tried to remember my best.
Yeah, that's okay.
But I think I'm scared.
You're scared?
Yeah.
Uh-oh. All right, are we ready to move on? Chapter 6. We're done with chapter 5. All right, chapter 6 is about the mole. Okay. Now, we talked a little bit about the mole, right? Yeah? No? Are you the mole? No. No, just kidding. The mole is the SI unit for the amount of substance. And when you guys are in lab, yeah? Do you have a device that measures the amount of moles?
Yes.
No such device.
Only electronic device.
So why is that the SI unit, right? Same thing with Kelvin. That's the SI unit, but we don't have a thermometer that measures Kelvin. Okay? And we use the mole so that we can make calculations, make predictions, really, how much product we're going to obtain, how much reactants we need in order to make a certain amount of product. And so we're going to learn Avogadro's number, which is, well, let's just talk about it. So 1 mole of anything is equal to 6.022 times 10 to the 23 representative particles.
One.
And this is just a conversion factor. If we want to convert moles to particles or particles to moles.
Representation of what? Representation?
Representative particles. Now, I'll tell you what that means in just a minute. Okay, so if we have 1 mole of carbon, what's a particle of carbon called? Does anybody know? An atom. The smallest particle of carbon that still tells us it's carbon. Okay? It represents carbon. Okay? So that means 1 mole of carbon is equal to 6.022 times 10 to the 23 atoms of carbon. So in this case, atom is the representative particle. You with me? Depending on what we're talking about, we might have a different representative particle. Another example, if we have 1 mole of water, what's the smallest particle of water that tells us it's water? A molecule of water, yeah, or H2O, 1 H2O, right? So this is 6.022 times 10 to the 23 molecules of water. Don't abbreviate the word molecule to MOL. Do you understand why? It'll confuse the heck out of you. Don't do it. Okay? Right? I know molecule seems like a long word, but don't abbreviate it. Okay? And then if we have 1 mole of sodium chloride, do we call that a molecule too? Most people call it a molecule, but it's not called a molecule. And I'm not going to test you on what it's called, but I'm just going to tell you what it's called. 6.022 times 10 to the 23 formula units of NaCl. Can we abbreviate formula units? Yes. No big deal, right? Okay. And then let's do one more. 1 mole of oxygen ions. What's the smallest particle of an oxygen ion that still tells us it's oxygen ion? It's still an ion. It's still an ion. So 6.022 times 10 to the 23 ions. Good? So those are the 4 different types of representative particles. I'll probably just call it particles for the most part. I'll use atoms and molecules. And do I care if you call this a molecule of salt? I don't. Most people do. It's not the right name, but
Your oxygen on either side are different, is that supposed to be like,
Oh.
what's the charge from the?
no, that's not supposed to be. There you go. Thank you. Okay, we good with that? So the representative particle here, atoms, molecules, formula units, and ions. Questions so far? And we just use this as a conversion factor. Because how many times do you want to know how many atoms are in your penny? Anybody just want to know that? Yeah, me neither. But it's kind of like wanting to know how many seconds old you are. Anybody care how many seconds old they are? I reached 1 billion. Okay. But we don't care about that. So why do we deal with this stupid yucky number?
It's medication.
So, no, we don't deal with it in medication either.
Pharmaceutical, when they,
Do we care how many atoms we give the patient?
no, not patients, like pharmacists.
They deal with grams and milligrams and micrograms maybe. But let me show you why we do this. And for this test, for this exam, we're going to have to be able to convert moles to particles and particles to moles. We will have to. It's on the test. But after this unit, chemists don't care how many particles there are in it. This is huge. Who cares? Okay? But this number, this Avogadro's number, 6.022 times 10 to the 23, this is pretty profound, okay? If we have water, H2O, let me use a different color here. There's 2 of what to every 1 of what? 2 hydrogen what? Atoms to every 1 oxygen atom. You with me? We all know that, okay? So the ratio is 2 hydrogen atoms, or I'm going to write it a little bit differently. 2 atoms of hydrogen to every 1 atom of oxygen. And so let's convert atoms into moles. Here's the conversion factor right here. What goes on bottom? Atoms, hydrogen atoms, right? And what goes on top? We want to know how many moles, right? So we're just converting hydrogen atoms to moles of hydrogen. You following me? So 1 mole of hydrogen is how many hydrogen atoms? 6.022 times 10 to the 23. Atoms of hydrogen. What cancels? Atoms of hydrogen. And guys, it's going to be to your advantage that you be organized this way. Write everything out. We talked about it in dimensional analysis, right? This is dimensional analysis. Include your units. If you don't, you're going to make a mistake. In fact, I was getting a lesson ready for my 1210 class, and I was just practicing some problems, making sure I'm refreshed on it, you know. And this isn't for class. I'll just rush it through, right? I got them wrong. And the reason I did everything right, but the unit of energy in that problem was kilojoules, and the other unit of energy in my dimensional analysis was joules. And they didn't cancel. Therefore, my answer is going to be wrong. Okay? We're not dealing with kilojoules and joules in this class right now. But keep organized. It will help you in the long run. Okay? All right, so let's do this. Do you guys know how to put these big yucky numbers in your calculator? Did we go over this yet? Okay. Let me show you how to type this in your calculator. Get it out and practice this. Because you want to get this right on the exam, right? Okay. And I'm not going to type it in for you. You've got to be able to do this. So in your calculator, we're going to start with 2. Well, because that's what we start with, right? We have 2 atoms of hydrogen. And then I'm going to push multiply or divide. Divide because this number's on the bottom, right? So I'm going to push the divide button in my calculator. Then I'm going to type this number. And here's how there's more than one way to type this number. I'll show you the way I do it. If you have your own method and it works, great. Okay? 6.022, just like normal. I'm not going to push the multiply button. Instead, I'm going to push on most TI calculators, it's EE. On most Casio calculators, it's EXP. And on some calculators, it's times 10 to the x. Okay? And then we put the exponent, 2, 3. And then you push equals. And we should get 12.044 times 10 to the 23. Is that right? Oh, no. Sorry, I multiplied in my head. This is why you don't do it in your head, guys. Divide. And what do we get? 3.32 times 10 to the 23. It shouldn't be negative. Oh, wait, yes, it should. Yes, it should. Oh, my gosh. This is why you don't do it in your head, guys. Moles of hydrogen. Not very many, right? Yeah. And that one that calculator right there, you have to make sure after you push the, in fact, on this problem, it probably won't make a difference. But if you keep doing more calculations, you have to push over, get off the exponent so that you can type something else. So second EE.
And 23.
Yep, that's it.
Yes, thank you.
Does anybody else need help with their calculator? Yeah. So second and the button right above number 7. So you have to put, so 6.022. And then push the second button. Nope, the one above, the white one. The top left button. That one right there.
Oh, okay.
And then you push the button right above the number 7. You see it says EE on writings right above it? That's how you access it on that one.
Okay, and then you just.
And then
write down
23.
what I'm
Yep. Yeah, Mariana.
Oh, I got it.
Oh, yes, I got it. 23.
I think, let me check. That's what Chad got. Let's see if he was right. All right, so we got 2 divided by 6.022 times 10 to the 23. Yeah, 3.32 times 10 to the negative 24. That's because you added. No, you didn't.
No, I didn't.
Okay. So you plug this in a little bit different. Order of operation has to be followed. Well, not really, because you're just multiplying and dividing, right? But your calculator, Mon, you have to probably, if you use parentheses, guys, it'll always work, especially for your calculators. Okay.
We figured it out. We're doing great.
Here, I use this.
Uh-huh.
I use this.
Uh-huh.
Correct?
Yep.
23. Enter. Yeah, I
You
got
gotta put parentheses.
it. Yeah, but I got it not the same.
I know, you gotta put parentheses around it. Let me show you. So do 2 divided by parentheses. 6.022 times 10. Oh, that's because I put the parentheses. So 2 divided by parentheses, 6.022 times 10 to the 23, and you have to push this over to get out of the edge.
I have to take all of
Yeah, you
this
gotta
and
put
parentheses.
parentheses around the
Then you practice
6.022 times 10 to the 23.
Divided. After divided, you have to put in parentheses.
Yeah.
Start parentheses, 6.
And the reason why, let me just show you why it's not working on some of your calculators. Because if you do 2 divided by 6.022, and then sometimes your calculator will say it's times 10 to the 23. That's what your calculator is doing for some of you.
My button, what I do is do, and then press this button, because then it makes it a fraction. So press this, and then you can type in the 6.022 on the bottom.
Oh, perfect. Thank you.
So that's 2.
Are we good?
So 6.022. So
Once we learn our calculators, then we should be golden, right?
and then do times
Okay, ready to move on. And this is the hardest part about this conversion.
the little up
So if you got it, no big deal. Thanks, Lucas.
Yeah.
All right. Are we good there, guys? Okay, now let's convert so that this water is 2 atoms of hydrogen to 1 atom of oxygen. We converted 2 atoms of hydrogen into moles of hydrogen. Now let's convert 1 atom of oxygen into moles of oxygen the same way, right? 6.022 times 10 to the 23 atoms of oxygen to 1 mole of oxygen. Atoms of oxygen go away, and we're left with 1 divided by 6.022 times 10 to the 23, and what do we get?
1.66 into 10 minus 24.
You with me? So what's the ratio of atoms of hydrogen to atoms of oxygen? 2 to 1, right? You with me? What's the ratio of moles of hydrogen to moles of oxygen? Well, let's see. Isn't it the same as this one divided by this one? Well, it cancels. Oh, not the whole thing, sorry. Just that number, right? It's still 2 to 1. So it's 2 atoms of hydrogen to 1 atom of oxygen. It's also 2 moles of hydrogen to 2 moles of oxygen. So instead of using 6.022 times 10 to the 23 all the time, we can just use moles. That's the profound thing with Avogadro's number. He figured that number out. It's the same ratio for every single element. So if we have 1 mole of sugar, how many particles of sugar do we have? No one knows? 6.022 times 10 to the 23 particles of sugar. And it's going to fill a container that much-ish. If we had 1 mole of water, how much water would we have? Still 6.022 times 10 to the 23 molecules of water. But we're going to have this much water. Why is that?
Because we are not thirsty.
Sugar molecules are larger than water molecules. But we still have that number of particles. You with me? So we still need to know how to convert moles to particles for this exam. But afterwards, we don't use it. You with me? So let's try some more examples. If we have 7.303 times 10 to the 24 atoms of gold, I want to know how many moles of gold. So what do? Dimensional analysis, that's it. 7.303 times 10 to the 24 atoms of gold, and I know, just write it all out. I know it takes a while, it's like, write it out completely. And we know for every 1 mole of gold, we have 6.022 times 10 to the 23 atoms of gold. Atoms of gold go away. We're left with moles. That's what we're looking for. Can multiply or divide. In this case, divide. And we should get 12.13 moles of gold. It'd be nice to have that much. So yeah, calculate that, make sure you can get that. Okay. And we could do another example.
Mole equal to A.
Yeah, do you see how the atoms go away? We're left with moles. What if we have 2.88 moles of silicon tetrachloride? And I want to know how many molecules of silicon tetrachloride I have. Can you do that without me setting it up? Or do you still need me to set it up for you?
1 mole we can put on the top.
Start with what we're given. 2.88 moles of SiCl4. What unit goes on the bottom? Moles. We don't want moles. We want molecules. See why you shouldn't abbreviate it? For every 1 mole of silicon tetrachloride, we get what? We have 1 mole of silicon tetrachloride. How many molecules do we have? Okay, 6.022 times 10 to the 23. That goes away. Now we multiply, because now it's on top, right? And we should get 6.94 times 10 to the 24 molecules of silicon tetrachloride. I know this is an icky calculation, icky number more. It's not a bad calculation, just multiply or divide.
I got 1.7.
Did I do it wrong?
I have no idea.
Well, let me
Maybe
double
I did
check.
wrong.
So 2.88 times 6.022 EE23. Yeah. 1.73 times 10 to the 24. Huh. Oh, that's because I did it a little bit different in my notes. Are we good there? Let's change it up just a little bit. What if I don't care how many molecules? I just want to know how many chlorine ions I have. Not ions. How many chlorine atoms I have. Can we do that? All right. So we know we have 1.73 times 10 to the 24 molecules of SiCl4, right? I don't want to know how many molecules. I want to know how many chlorine atoms I have, right? If I have one molecule, why do I put molecules on bottom? So it cancels out. How many chlorine atoms do I have if I have one molecule of silicon tetrachloride? 4. Do you understand that?
Yes.
4 chlorines to every one of these. Do we get that? So now molecules cancel. And then we get 6.94 times 10 to the 24 atoms of chlorine.
94 or 6?
94. Type it in your calculator. Make sure you know, you can do this. Yeah, Lucas.
We were asking for atoms of silicon that would be equivalent to the first number.
That's right, because it's a 1-to-1 ratio. Uh-huh. Yep. Good.
Oh wait, the number of atoms of silicon would be the 1.73 times 10 to the 24.
Yeah, so that's molecules of silicon tetrachloride.
The same as,
Oh, and if we did atoms of silicon?
that's
Yeah, because it's a 1-to-1 ratio. Yes. Uh-huh.
Here that you wrote one molecule size for, we already know one molecule is 6.
Yeah. If we have one of these, we have 4 chlorines.
4 chlorine, but on one molecule of SiC is 6.022.
No? No? We don't need to do that anymore. We already did that right here.
But we already know this, so always one molecule is that one more.
For this problem.
Yeah, but
If we had, let's say we have magnesium nitrate. If we have 1 mole, this will answer some of your questions here. If we have 1 mole of magnesium nitrate, question.
I get 92 instead of 94.
92?
Yeah, 6.93.
Okay, maybe. Just a rounding difference. Okay. And so here, I started with this number, or you started with this number. But if we started with this number and just kept converting until we ended up with atoms, you'd probably get my answer. Because this is a rounded answer, right? And that's why it's slightly different. Okay, so if we have 1 mole of magnesium nitrate, how many formula units of magnesium nitrate do we have? Y'all with me? We have 6.022 times 10 to 23 because that is 1 mole. That's what 1 mole means. 1 mole of anything is 6.022 times 10 to 23. How many magnesium atoms do we have?
6.022. No,
Just one.
How many magnesium atoms do I have in 1 mole of this stuff? 6.022 times 10 to the 23 because it's a 1-to-1 ratio. You with me? How many molecules of nitrate do I have in 1 mole of magnesium nitrate? 2 times this, right? So 12.044 times 10 to the 23. I know that's not in scientific notation, but okay. You with me? What if I said, how many oxygen atoms do I have? 6 times that. You with me? Am I confusing anybody? Because there's 6 oxygen atoms for every one of those. You with me? So this is dimensional analysis. It's no different than converting inches to feet. We just have a yucky number to deal with. That's it. Okay, the conversion factor is not 1 to 12 for inches to feet. It's 1 to 6.022 times 10 to 23. That's it.
So what's so magical about that number? Like, I guess
It doesn't matter what substance you have. If you have 1 mole of Andrews, guess how many Andrews you have? 6.022 times 10 to 23 of them. Well, that's a lot of Andrews. Okay? It doesn't matter what it is. If you have 1 mole of anything, it's 6.022 times 10 to 23 of that thing.
So I guess that's why in my mind it's like, why does it have to be that number and why couldn't it just be something
Why does it have to
like
be?
that number?
Because it is that number.
Okay.
But why is it? That's the question of the universe.
All right.
It is. And we found that it is. We discovered that it is. Well, we didn't. Avogadro did. He discovered that's what it is. And since we know that, now we can make better predictions. And that's where we're getting. Okay? Are we okay with converting moles to particles or particles to moles? Just one conversion right there. That's it. Okay, do you remember atomic mass? What is the unit of atomic mass? Yes, it is AMU. Just like this is 5 distance units. That's stupid, right? No, it is AMU. You look at every chemistry book and they say it's AMUs. That's right. Atomic mass unit. But what is the atomic mass unit? grams per mole. That's what it is. So everybody get your periodic table out. What's the atomic mass of oxygen? 16 what? Grams of oxygen per 1 mole of oxygen. That's a conversion factor. You with me? What's the atomic mass of carbon? 12.01 grams per mole. That means if you have 1 mole of carbon, it's going to have a mass of 12.01 grams. Not 1 atom of carbon, right? 1 mole. And so all of the atomic masses are just conversion factors. A lot of conversion factors we don't have to remember. We just have to look up, right? Okay? Does that make sense to everybody? Now that's great if we're dealing with just single elements. But a lot of times we're dealing with compounds, yeah? We got to deal with molar mass. This is the mass. Uh-oh. The mass of 1 mole of whatever we're dealing with. What is the molar mass of water? Did we learn this already, kind of? Remember, if it has the same intermolecular forces and we want to know which one has a greater melting point, we have to look at the masses, right? That's what molar mass is. So what's the atomic mass of hydrogen? 1.008. We have to multiply that by 2 because there's 2 hydrogens. Plus, the molar mass of oxygen is 16. We add those together and we get 18.016 what? Grams per mole. That is the molar mass of water. So we can measure grams in a lab, right? We can convert grams into moles using the molar mass. Does that make sense? This is just a conversion factor. The conversion factor is 18.016 grams of water for every 1 mole of water. And if you want, you can flip that depending on what you start with and what you're converting to. You with me? Any questions on that? Should we do one more? Sugar is C12H22O11. Let's find the molar mass of sugar. We find the atomic mass of 1 element at a time. What's the atomic mass of carbon? 12.01. And again, we can round this if we want to 12, but that's not our final answer yet. Let's don't round until we get to our final answer, yeah? Let's multiply that by 12 because we have 12 of them. And we're going to add to that, what's the molar mass of hydrogen? 1.008 multiplied by 22 because there's 22 of them. And we're going to add to that 16 multiply 11. So we get this is 144.12. And this is 22.176. And this is 176. And all of that together is 342.3. 30 grams per mole. So now we can convert grams of sugar, which we can measure in a lab, into moles. Why? So we can figure out how much product we're going to get if we melt sugar and it goes down into carbon and carbon dioxide and water or whatever. How are we feeling? Are we overwhelmed or are we doing okay? Oh, I need to give you guys another worksheet, don't I? Yeah, sorry. I need to give you guys another one. Sorry, I put there to get some down each row, but I'm kind of handicapped, so.
Excuse.
The work line is 6 for the kid that right at CPs.
Thank you.
So, we already learned section 1. That's converting atoms into moles, or molecules into moles, or moles into atoms, or whatever. Section 2 is determining the molar mass. Let's do a hard one, shall we? Which one on this section 2 looks like, that's yucky?
That's the one.
HCH3CO2? All right. We could do one step at a time, or we can see, how many hydrogens do we have? 4. 1.008 multiply 4. Does everybody follow me? How many carbons do we have? 2. So 12.01 multiply 2. You understand where I'm getting the 12.01, guys? Okay. And the oxygen, 16 multiply 2. We add those together. 1.032 plus 24.02 plus 32. $57.052, and we can round that if we want. Oh, did I do it wrong? Oh, that's because this is a 4. My bad. Yeah. About 60, right? 60 what? Grams per mole. You can write 0.1, no big deal. Okay, when you do this, this is just an intermediate step, right?
What is that, 60 grams?
Okay. Calculate twice, post once, right? Yeah.
Could you do ammonium, NH4?
Yep.
In parentheses.
If you can tell me what it's called, I will.
Ammonium sulfate.
There you go. All right, I'm just teasing. So you got NH4, 2SO4, right?
So you multiply the 2 into ammonium.
So all of this stuff, right?
Yeah.
Yeah, so we're going to have 14.01, which is the atomic mass of nitrogen. And how many nitrogens are there in this whole compound?
2.
2 of them. Good.
And then 8 hydrogens.
And there's 8 hydrogens, so 1.008 multiply 8 plus 1 sulfur, that's 32 point what?
Oh, seven.
07? 32.07 and 16 multiply 4. That's it. We know how to add these. We just did this with balancing equations, right? Any questions on molar mass? Do you want to do any more together? Okay. So now let's use the molar mass as a conversion factor. If we have 1.58 grams of sodium chloride, and we want to know how many moles of sodium chloride do we have? So what do we do first? Yeah, start with what we know, 1.58 grams of sodium chloride. Do we want grams in our answer? No, so where does it go? On bottom. And we're looking for moles. Do we know a grams per mole conversion factor? Is it 6.022 times 10 to the 23? That's moles per particles. This is grams to moles. Where do we find the conversion factor from grams to moles, moles to grams? Molar mass. So we got to find the molar mass of salt. 22.99, is that right? Don't memorize these guys. Okay. Plus chlorine is 35.45. How do I have these memorized? We use them all the time. Okay. And so we get 58.44 grams per mole. So where does the 58.44 go? Did I calculate that correctly? Yeah. Goes on top or bottom? It says 58.44 grams per 1 mole. So 58.44 grams per 1 mole. You with me? Grams goes away, we're left with moles. That's what we're looking for, so we can stop converting. And we get 0.027 moles of sodium chloride. So now you know where to find a whole load of conversion factors from grams to moles, moles to grams, yeah? How are we feeling? Can we do this? If we have, let's do another example. If we have 2.45 moles of carbon dioxide, and we want to know how many grams we have. What do we do first? What? Yeah, we can find the molar mass first. Yeah. Carbon is 12.01, plus there's 2 oxygens, 16 apiece. So that's 44.01 grams per mole. You follow me, or am I doing it too quick? Talk to me.
Slow down a little bit.
Okay. Do y'all understand where I'm getting these numbers from?
Yes.
So yeah, so can you do this? That's what I'm asking. We good? So now I'm going to start with what I have been given, 2.45 moles of carbon dioxide. Do I want moles in my answer? No, so where does it go? How many? 1 mole of carbon dioxide has a mass of 44.01 grams. Moles go away, we're left with grams, that's what I'm looking for, so I can stop converting. You see, this is just dimensional analysis, guys. When I say just, I'm not saying it's easy, but we learned this way back when. That's all we're doing. That's the majority of all chemistry math for this class. Okay? All right, so we multiply and divide those, or just multiply in this case. 107.82 grams of carbon dioxide. Well, if I did sig fig, we're not doing sig figs in this class. Never mind. That's good enough. We have 2 decimal places, so just round to 2 decimal places. Good? How are we feeling with this? Yay or nay? Good? Okay. Do you want to try another example, or should we move on? Talk to me. What do you need? Okay, I'm here and moving on. Okay? So I would definitely practice it on this sheet, okay? But let's move on. Let's talk about stoichiometry. That sounds icky, right? That sounds like math on steroids, right? All right, so stoichiometry is basically the quantitative relationship, meaning with numbers, quantitative relationship between reactants and products in a chemical reaction. Those are just words. Yeah. So that we can convert grams of one substance to grams of another substance. How do we do that? With moles. Okay? This is the last conversion factor we're going to learn for this unit. And then we just convert. That's all we're doing. All right, so we got to have a chemical reaction. So let's take C3H8 plus oxygen. So this is propane. You burn propane in the presence of oxygen. We're going to get carbon dioxide and water. What type of reaction is this? We've got 3 types: oxidation reduction, precipitation, or acid-base. What would your guess be? So it's a redox reaction because it's not a double replacement reaction. Okay?
How do we know it's not double replacement?
Because this is not an aqueous solution. This is not an aqueous solution. Well, I didn't tell you. But how do you know it's not aqueous? It's not an ionic compound. And they don't have partners to swap, and they don't do that. So That's how we know. Okay? All right. So let's say, well, first of all, before we can do stoichiometry, we have to do one other thing. We have to balance the equation. Otherwise, what we're doing is worthless. Okay? You must have a balanced equation. So if we do this, 3 carbons, 3 carbons. Y'all with me? 8 hydrogens. Put a 4 right there, so we have 8 hydrogens. Now let's count the oxygens. We have, this is supposed to be an O. There we go. We have 6 oxygens plus 4 oxygens. That's 10 oxygens on the right. What number goes there? 5. Good? All right, now in our balanced equation, we have more conversion factors. I'm going to show you how to find them. The coefficients in our balanced equation represents the number of moles. Now, it doesn't mean we have to have 1 mole of that and 5 moles of that in a reaction. We could have 3.26 moles of propane, right? But this just tells us, well, let me just tell you. A chemical reaction without balancing is a is a ingredient list. Can you guys make Oreo cookies by just looking at the ingredients on the Oreo package? If you can, you're good, right? Okay. But eventually people get it. They trial and error until they get it, right? But better than an ingredient list is a recipe. A balanced equation is a recipe. This tells us for every 1 mole of this, we need 5 moles of this. And we will get 3 moles of carbon dioxide, and we'll get 4 moles of water. So here's our conversion factors. 1 mole of C3H8 for every 5 moles of oxygen. That's one conversion factor. And we can flip it, right? Depending on what we're starting with and what we're going to. 1 mole of C3H8 to every 3 moles of carbon dioxide. You understand where I'm getting these numbers from? Then you tell me the next one. 1 mole of C3H8 to every how many moles of water? 4. That's the coefficient in front of water. And the 1 is the coefficient in front of C3H8. Do you all follow me? Talk to me if you don't. Yeah, Andrew.
So just to clarify, I'm not sure how to put it. The first one is because they're reactants.
No, it doesn't matter if they're reactants or products. All we're doing is looking at the coefficients in front of these substances. There's 1 of those to every 5 of those. There's 1 of those to every 3 of those. 1 of these to every 4 of these. That's it. So there's 3 of them. We could also flip those and get 3 more. Do you need me to write them down? Yeah? Okay, so we flip this, and we get 5 moles of O2 for every 1 mole of C3H8. You see how I just flipped that? And we got another conversion factor. We can flip this one when I get 3 moles of CO2 to every 1 mole of C3H8. And 4 moles of H2O to every 1 mole of C3H8. Are there other conversion?
Sign between them, you put I.
This is just a semicolon. That what you're asking?
And
Just to separate them. Yeah.
Could we also say, for example, that for every 3 moles of carbon dioxide, you have 4 moles of H2O?
We sure can. And we can flip that one, right? And we can also say for every 3 moles of carbon dioxide, we have how many moles of oxygen? And we can flip that. And the last one we didn't do is 5 moles of oxygen to every 4 moles of water. And we can flip that. So we have a total of 12 conversion factors in this chemical reaction. And what does it convert to? Moles to moles. You with me? So we learned how to convert moles to atoms or atoms to moles, right? Or particles. We learned how to convert grams to moles and moles to grams. That's molar mass. And now we're learning moles to moles. Moles of one substance to moles of a different substance. We can go from reactant to reactant. We can go from product to product. We can go from reactant to product. Doesn't matter. Whatever we are interested in doing. Is this exact? If we're 100% correct, this is pretty close to exact, if not exact. So this is for making predictions. Pretty darn close predictions, if not perfect. But when we do it in the lab, will we get a perfect result? We're going to measure a little bit off, right? It's not going to be exact. So this is a prediction. Yeah.
So maybe you could repeat what you just said. So first we converted moles to atoms.
So moles to particles and particles to moles. That's using Avogadro's number, 6.022 times 10 to the 23, right? We good with that conversion? And then we use the molar mass to convert grams to moles or moles to grams. And it's not to kilograms, it's to grams. If we wanted kilograms, what would we have to do? Convert grams to kilograms, yeah. By dividing by 1,000 or multiplied by 1,000, right? And then here we're learning how to convert moles of one substance to moles of another substance. So when doing stoichiometry, you must do this step. This is always going to be a part of it. Now, sometimes we may be given the moles of a product or of a reactant, and we want to know moles of a reactant. This is just one step, right? Sorry, product. Or we might be given grams. Most likely, we'll know the grams of reactant, right? And we want to know how many grams of product we'll get. How many steps is that? First, we convert grams to moles, then moles to moles, then moles to grams. 3 steps, max. Would you like a mole roadmap? Get your periodic table out that you get for the exams. There's one on that sheet. It's on the back side, and it looks something like this. Oh, that's it. That's all I have for you. Do you want me to write it out, or should I explain how to use it real quick? So we got grams of substance A. That could be our first substance we're going to. We got to convert that to moles of substance A. We could also convert moles of substance A into particles of substance A. You following? If we want to go to a different substance, we go from moles of substance A to moles of substance B. Then once we're at moles of substance B, we can convert that into grams of substance B, or we can also convert it to particles of substance B. Do I have it this way, or do I have B on top?
Yeah, we have to.
Either way, right? Well, I can flip this whole thing and it still works. And then you got some other stuff over here. We'll talk about that in chapter 10. But this is the path. You find out where you are. So if you start at grams of some substance and you want to go to grams of a different substance, you follow this path. And it tells you on your chart what you do, right? This is molar mass. This one's molar mass. This is Avogadro's number. This is Avogadro's number. And what's in the middle? Mole to mole ratio found on the balanced equation. This is what we just went over. Okay, I'm going to stop there. Sorry I went a little over time. Practice those. We didn't do practicing to mole using the balanced equation. But why don't you try that? That is on section... That's on the back side of the worksheet. We'll do more next time, and then we'll get into chapter 7. Take care. Thank you.